All right, so now we're ready to talk about noise factor and noise figure, which are really the same thing. The idea here, let's start off with an active two-port. We can apply this to a passive two-port as well, but let's do the active case first. So we have an active two-port. It's shown by this box here. So this box has terminals on the right and on the left. And let's assume it's perfectly matched. Again, we can do the non-perfectly matched case as a separate problem. It gets a little bit more complicated because the impedance mismatch has changed the results. So initially we'll call it perfectly matched. And we can characterize this two-port then as having some gain, G, and some noise factor, F. And F is the thing that I want to define here. So let me show you how I go about doing that. First, I apply some signal power, P sub S here. So P sub S is signal power applied. And out the back comes G times P sub S, right? The signal power is increased by the gain of the two-port. Similarly, I have some noise power applied to this thing, P sub N. And the noise power that comes out, if there were no noise intrinsic to the two-port, would be G times P sub N. But this two-port has some noise intrinsic to it, internal to it. So what I get is a greater amount of noise than I applied, and that greater amount of noise is greater by a factor F. And obviously F has to be greater than or equal to 1, right? The noise can only go up. So on the left here, I can say what the signal noise ratio is. It's the signal power divided by the noise power, or just simply P sub S divided by P sub N. That's the input signal to noise ratio. The signal noise ratio at the output, similarly, is the signal power, which we just said was G times P sub S, divided by the noise power, which we just said was G times P sub N times F. P sub S times P sub N is the input SNR. We just showed that over here. And G cancels, so the only thing left over is F. So we find that the output signal noise ratio is equal to the input signal noise ratio divided by F. Said differently, F, the noise factor, is the ratio of the signal noise ratio at the input to the signal noise ratio at the output. And this is always greater than or equal to 1 because devices can only degrade signal noise ratio. They can't improve it. So the definition is actually on the bottom here. It's the ratio of the signal noise ratio at the input to the signal noise ratio at the output. And we call that F. F is noise factor. Now noise figure is really the same thing. We just express it in dB. So we take 10 times log base 10 of that same quantity, and that's noise figure. Now it's a little bit goofy here. This is a case where we call something by different names simply because we expressed it in dB. Nevertheless, it is traditional to do this. So noise factor implies a linear quantity. Noise figure implies the decibel equivalent of that linear quantity. To further confuse the issue, I will point out that people will frequently refer to noise figure as being either one of these two things. So as always, you should be very careful that you understand the definition of the thing that's being asked for, because people are sometimes a little bit reckless and don't always show you the units. So now we have these two things. We have equivalent noise temperature and we have noise figure. Now they must be related somehow. Let's try to make that connection. So here I'm talking about the noise temperature interpretation of what we just did. In other words, I'm going to repeat the previous problem, but now I'm going to do it in terms of noise temperature as opposed to invoking a noise figure. So once again, I have an active two-port, perfectly matched input and output. Its gain is G, but now it has an input referred equivalent noise temperature T sub EQ, right? I have some power spectral density at the input. That's the total power of the signal divided by the bandwidth of interest. I call that S sub N. The noise power density is the noise power divided by the bandwidth. And we know that we can express that as an equivalent noise temperature. And we'll call that K times T sub N. So the idea here is we represent the signal power as some power spectral density, which has units typically of watts per hertz. And then the noise is represented as an equivalent input noise temperature, T sub n. And in order for that to be also a power density, we have to multiply by K. So just remember K is joules per Kelvin, and T sub n is Kelvin. That gives us joules, but you also can see that joules is simply watts per hertz. They mean the same thing. In any event, that's how we're going to represent the noise. At the output, what we have is the signal power spectral density is increased by a factor G, the gain of this thing. And then what happens to the noise? Well, two things. First is that the noise that appeared at the input multiplied by K is increased by factor G, just like the signal was. But we also have internal noise, and we call this input referred internal noise, so it appears at the input of this ideal amplifier, and that is K times TEQ, again, units of watts per hertz. So in that case, this adds, and it adds TEQ times K times G. So I can factor out those common factors of G and K, and I get this expression. So this is the noise that appears at the output of this two-port. So on the left, on the input, the signal noise ratio is simply S sub n divided by K times T sub n. On the right, the signal noise ratio is S sub n divided by K times the quantity Tn plus TEQ, because again, those gains canceled out. Now, if I apply the definition of noise factor or noise figure, depending on how you want to refer to it, noise figure is signal noise ratio at the input divided by signal noise ratio at the output. And we just computed those two things. If we divide this by this and get rid of the common factors, we get Tn plus TEQ divided by Tn, and we see that we can rewrite that as 1 plus the ratio TEQ divided by Tn. So this expression tells us how equivalent noise temperature is related to noise figure. So now we have a way to talk about two ports in terms of either equivalent noise temperature, this thing here, or noise figure. We can do it either way because we can convert back and forth using this relationship. This raises the question of a reference temperature. All right, what I just worked out is noise figure is given by this expression, but this expression depends on the noise that we applied to the input. In other words, the relationship between noise figure and equivalent noise temperature depends on what noise I applied to the input. So you have to be careful about how to interpret what's going on here. Noise figure is not an intrinsic parameter of a two-port. In other words, to calculate the signal noise ratio at the input, I had to know what Tn is. And if I have to know what Tn is, then the associated quantity cannot be something which is intrinsic to the two-port. The equivalent noise temperature, on the other hand, does not depend on this input temperature. To further confuse the issue of how noise figure is defined, I will tell you that it is common to redefine noise figure or noise factor as an intrinsic parameter, and the way that's done is by requiring that input noise temperature to be equal to some standard value, which we refer to as the reference temperature. The reference temperature for noise figure plays a role which is very similar to the role played by the reference impedance in determining S parameters. That's a pretty good analogy. Reference temperature is almost always defined to be 290 Kelvin. That is the IEEE standard. But again, it could be defined to be any value. It could also be defined to be the physical temperature. It could be defined to be absolute zero. There are many ways to define the reference temperature, but the vast majority of the time it's defined to be 290 K. There's no wrong answer here, but 290 K is the most commonly used reference temperature. So now I can rewrite noise figure as 1 plus TEQ over the reference temperature. and then I have to say what the reference temperature is. So let me roll this up for you one more time. TEQ, the equivalent noise temperature, is intrinsic. You need to know nothing else to know what that means. But the noise figure of a two-port depends also on this reference temperature. So if somebody tells you what the noise figure of something is, you better make sure you know what the reference temperature is. I can also now get the equivalent noise temperature in terms of the noise figure just by rewriting this equation, and here it is. So I take the noise factor, that's the linear quantity, not the quantity in dB, the linear quantity. I subtract 1, and then I multiply by the reference temperature, and that gives me the input referred equivalent noise temperature. I finally note here that confusion about whether a particular value of noise factor or noise figure uses the actual input noise temperature or this reference temperature of 290K results in a lot of errors in common practice. Usually those errors are quite small. Every once in a while those errors become significant, so you should be careful that you're not making this mistake. So here's an example. Let's say an amplifier has an input referred equivalent noise temperature of 250K. So this is TEQ. What is the noise factor? And then what is the noise figure by the common definitions? So this is a good place to stop and see if you can come up with the answers to these questions. Okay, here's the answer. First, assume 250K is the input referred equivalent noise temperature. It didn't say it here, but that's how we've been talking about it. So let's assume that that's the case. Then let's assume that the reference temperature is 290K. If we do that, then we find that the noise factor, 1 plus the ratio of TEQ to T naught, is 1 plus 250 over 290K, which is 1.86, and that's the noise factor. To get the noise figure, I take 10 log 10 of that number, and I get 2.7 dB. That's a very typical kind of noise figure for an RF amplifier. Now note that the minimum noise factor, or minimum noise figure, depending on how you think about it, is 1 in linear units or 0 in dB. This is one way you can check your work. If you find a noise factor which is negative in dB or which is less than 1 in linear units, you know something has gone wrong. I'll also point out here that a typical definition for a low noise amplifier, frequently referred to as an LNA in this business, is one which has a noise figure of less than 4 dB or so. Again, this is not a formal definition, but generally if you see noise figures for amplifiers which are less than about 4 dB or so, they are referred to as low noise amplifiers. Not a rigorous definition, just a common way of talking about those things. Now, as I promised before, we can also use this concept to address noise from passive two ports. Let me show you how that's done. Here's a passive two port, perfectly matched at the input and output. The gain must be less than 1 because it's passive. Input referred equivalent noise temperature, TEQ. So I have the following picture. I have gain here. I have noise power spectral density being applied to the input. And then at the input, I have a signal power spectral density and a noise power spectral density. So at the output, the signal power is increased by gain. The noise power is increased as follows. The input noise is increased by a factor of G, and then we add the input referred equivalent noise temperature. So we get this expression, and this was all the same as before, but now we can use thermodynamics again. If we assume thermodynamic equilibrium, which generally just means that everything here is at the same temperature, then I know that the power delivered to the output must be K times the physical temperature. So if you've had a course in thermodynamics, you know immediately why this is true. If you have not had thermodynamics, don't panic. This is a very simple idea. The idea is simply that if everything here is in thermodynamic equilibrium, in particular if it's all at the same temperature, then I know that the noise that must end up delivered to the output is K times the physical temperature, given the assumptions I've made here. And that tells us how to compute now what's going on for this passive two-port. TEQ now we can compute as the physical temperature minus the gain times the input noise divided by G, the gain. And simplifying that expression, we get this. We find that the input referred equivalent noise temperature must be the physical temperature divided by the gain minus the input equivalent noise temperature. And then the noise factor is just 1 plus TEQ, which I just worked out, divided by T sub n, and that gives me this expression. So the noise factor for a passive 2-port is simply the physical temperature divided by the input temperature divided by the gain. Very, very simple concept. Now here I've written that expression again. I want you to note a couple things here. First, this increases with increasing loss. 1 over gain is loss. So when loss goes up, the noise figure also goes up. So for example, if we have a cable being a passive 2-port, and the loss in that cable is increasing, then the noise factor of that cable is also increasing. Similarly, if I have some cable and it's at some temperature and thereby produces a certain amount of noise, and I increase the temperature of that cable, then the noise will increase and the noise factor will increase. Now here's an idea which is important to note because it's so often used. If we assume that the applied input noise is equal to the physical temperature, which by the way it will be if everything is passive and at the same temperature, in other words in thermodynamic equilibrium, then T phys over Tn are equal. And if they're equal, then this expression just becomes 1 over gain. Now this is the equation which is most often simply shown when discussing the noise factor or noise figure of passive 2-ports. It's simply said to be 1 over gain. But you see that this idea actually has a whole bunch of assumptions tied to it. So you have to be pretty careful, right? This is true if everything's in thermodynamic equilibrium. So now perhaps you also see why the reference temperature for noise figure is chosen to be 290 K, or to be more clear, it's chosen to be something around room temperature. If you choose a reference temperature to be around physical temperature, then this ratio will be very, very close to 1. And then you'll get this at least approximately. Now I have to warn you, electronics get hot. Perhaps you already know this. So physical temperature much, much greater than 290 Kelvin is pretty common. So the extent to which you can say that because you have this reference temperature, you have approximately this condition, sometimes that can get iffy. So be very, very careful if you're going to use this. Let me show you an example to show you in numbers what the issue is. Let's say we have some coaxial cable. And let's say the loss on that cable is 2 dB. In other words, if I apply signal and everything's matched, the power at the output is 2 dB below the power at the input. And let's say the physical temperature of that cable is 19 degrees Celsius, which by the way is 66 degrees Fahrenheit. Then you can ask, what's the noise figure? In fact, this is a good time to stop the lecture and see if you can work that out. All right, you ready? Here we go. The answer is it depends. We know that the gain is minus 2 dB. That's 0.631 in linear units. 19 degrees Celsius is 292.1 Kelvin. If you take the reference temperature to be 290 K, as is the IEEE preference, then you find that the noise factor is 1.6, which is 2.03 dB. If, however, you take the reference temperature to be 292.1 Kelvin, which is the actual physical temperature, then you get the simpler expression. The noise figure is equal to 1 over gain, and you get 2 dB. So you see, if you're not careful here, you could introduce 3/100ths of a dB of error, even though everything is around room temperature, right? If the temperature is much greater, the difference between these two things can grow. Right? Now, this is not a design error. This is simply an error in your application of the definition. So this is where you have to be careful. Right? The answer to the question is, it depends. It depends on how you define noise figure. Noise figure depends on reference temperature. If you're going to say what the noise figure is, you had better make sure there's a common understanding about what the reference temperature is going to be. This concludes this lecture on Introduction to Noise.